some more graphing problems from section 4.6. Start all your graphing problems by deciding what the domain is. You don't want to be looking for critical points or other points that are outside your domain. So in this case, what would be the concern about this function? What could go wrong? Yeah, you could have a negative under the square root. So we want to make sure that the square root always has a positive number or at least 0. So I want to make sure that 9 is greater than 9 minus x is greater than or equal to 0, or 9 is greater than or equal to x. It might be easier to flip that around as x is less than or equal to 9. I think it's a little friendlier to see things that way. So whatever the values of x are, they have to be less than or equal to 9. Now let's see. There's no symmetry. This is not an odd function. It's not an even function. So we don't get any free passes that way. There's no numerator and denominator of this function, so we're not going to get some easy asymptotes. In fact, there's not going to be a horizontal asymptote nor a vertical asymptote. So what next then? Well, let's start trying to find where the function's increasing and decreasing, and also concave up and concave down. In order to do that, what do I need? Derivative. And in differentiating this, what rule do I have to use? Product rule and the chain rule. Good, we're going to have to use a chain rule when we differentiate this part. So let's use the product rule first. G prime is going to be derivative of the first times the second plus the derivative of the second times the first. So it's going to be x times 1/2 9 minus x to the negative 1/2. But I'm not quite done. What else do I need here that's part of the derivative of this term? Got the derivative of the outside times the derivative of the inside. Thank you. And the derivative of the inside is negative 1 there. So we'll clean this up a little bit. It's 9 minus x to the 1/2 minus 1/2 x times 9 minus x to the negative 1/2. And let's clean that up a little bit more. You may recall seeing something like this before in our work. When you have these fractional exponents, particularly when they're negative, or even if they're not negative, they're positive, it's helpful to factor out the most negative term or the smallest of these terms. So in this case, I'm going to factor out this term as part of a GCF. So 9 minus x to the minus 1/2. Now I'm going to show all the gory details involved in this. Some of you might be good enough that you can skip this, and that's fine. In fact, I'm sure that if you do enough of these in terms of practice, that you will get good enough. Now in both parts of this, when I'm factoring this term out, I'm going to divide each of these terms by that factor. And that's going to lead to some nice simplification. Let's start with the simplification here. That 9 minus x to the negative 1/2 term cancels out all together. As far as the other part is concerned, again, I'm going to get some nice simplification. But you've got to be a little bit careful in order to get that. We have to subtract exponents here because we're dividing things with the same base. What do I get when I take 1/2 minus negative 1/2? 1. Yeah, thank you. We get 1. So, all right. So 9 minus x to the negative 1/2. That's going to be 9 minus x to the first power minus 1/2 x. And here I've got like terms. So let me combine the like terms. And I'm also at the same time going to put this into the denominator. let me point out that the coefficient of x here is a -1, and that there's really like terms that I'm going to add. I've got a -1 here and a -1/2 there. What's -1 plus -1/2? -3/2, right? So, you see that? Okay. Okay. All right, so what we're left with then is 9 minus 3/2 x over 9 minus x to the 1/2. Or you could write that or think of that as the square root. That's our first derivative. That's g prime of x. So the question is, where is the first derivative equals 0, or doesn't it exist? In other words, where could it change signs? This function can change signs where the numerator is 0 or where the denominator is 0. Yes, sir?
I got a little lost. Where'd you get the 9 minus x to the -1/2 that you put outside the brackets?
Oh, that's what I chose to factor out right here. So I said, let's factor that out. Now, when you factor something out, you end up dividing both of those terms by that factor. It's something that we don't think of too often. But for instance, if I gave you 7x plus 21, instantly you could factor that and say, okay, that's 7 times x plus 3. But what you're really doing, even though you don't see it, is each of these factors is going to get divided by that term that you're factoring out. So if I divide both of those by 7, you can see, oh, okay, those cancel, I get this. Those cancel, I get that. We're doing the same thing here. I'm factoring out that term with a negative exponent, so I have to divide each of those terms by that thing right there. All right, it's the tricky part, and that's why I like doing this a couple times, because it does take a little bit of work to get comfortable with that. But we need that because when we get it in this nice form, it's going to be easier to find the second derivative, and it also helps us decide where these terms can equal 0. So, sure. Where can these terms equal 0? Well, let's figure that out. Let's work with the numerator equals 0. That'd be 9 minus 3/2 x equals 0. Let's move the 3/2 x to the right-hand side for the simple reason that that makes that a positive 3/2 x. And the shortcut to solving here would be to multiply both sides by the reciprocal, 2/3, and get 6 for x. So x equals 6 is a place where the derivative can change signs. How about the denominator equals 0? Where does 9 minus x to the 1/2 equal 0? Yeah. If you're not comfortable with this, you could square both sides. Square both sides and get 9 minus x equals 0. Or somebody forecasted a little while ago that x equals 9. There's a little bit of a problem, though, with x equals 9. It's right at the edge of your domain. You're not going to get any changing of signs when it's right at the edge of the domain. So, okay, that's fine. The function really can only change sign in the derivative at one point, at 6. So let's take care of that right here. So x, g, and g prime. And then at x equals 6, at x equals 6, the function has a 0 derivative. But let's test points on either side of x equals 6. So what are some good test points for us? All right, 5 and 7. 5 and 7 are some good test points. You can take out your calculator to test them. Really, I mean, I guess the very minimum we need to do is test it in the numerator. That's going to dictate the sign of the derivative. If we test it at x equals 5, I think it's going to be positive. Double check me on that. Yeah, it's going to be positive and then negative. So what's that tell us about our function? Increasing, then decreasing. What kind of point does 6 have to be if the derivative is increasing and then decreasing? It's a maximum. Good. So this is a maximum at x equals 6. Nice. Let's work with the second derivative then. And I don't want to spend all my time calculating derivatives here for you. So I'm just going to give you the second derivative. You'd have to use the quotient rule and play around a little bit. So let me just give you the second derivative. G double prime of x, and this has already been cleaned up, is going to be 3 times x minus 12 over 2, over 4 times 9 minus x to the 3 halves. All right, so I've done some work to clean that up for you a little bit. We have to ask ourselves the same kind of questions, and that is, all right, well, where does this thing change signs? Or where could it change signs? So that's going to be where the numerator equals 0 or where the denominator equals 0. So where can this change signs? All right, so the numerator equals 0. 3 times x minus 12 equals 0. That's going to happen when x equals 12. How about the denominator equals 0? 4 times 9 minus x to the 3 halves equals 0. 9 minus x to the 3 halves equals 0. Can you see that there's only one place where this is going to equal 0? X equals 9. Which, again, that's at the edge of our domain. We're not going to get any changing of signs in the derivative there. But how about 12? What about 12? Yeah, thank you. 12 is outside the domain completely. It's not even close to being in the domain. And this is why you need to look at the domain here, because we don't want to be playing around with the function at x equals 12, because there is no function there. It's outside the domain. So really, the second derivative is either always positive or always negative. And you can test any point you want. So let's make ourselves the traditional little table, g, x, g, g double prime. And we'll do it this way. Any. You can test any point you want in the second derivative. Now, if it was me, I'd probably try and make it easy. So what would be an easy value to plug in here into the second derivative? 0, sure. And if you plug in a 0, what do we get? We get something negative, right? You get, so at x equals 0, g double prime of 0 would be negative 36 over 4 times 27 is what, 108? But the bottom line, even if my arithmetic's wrong, is that it's negative. It's clearly negative. So second derivative is negative. What's that tell me about my function? Concave down. Good. Concave down. Yes, sir.
Now, if we ended up with a number like instead of 9, it was a 7, then in that case we'll do the same thing. We'll test like a number before, before and number after,
Yes. Yeah.
and then check and see if it's concave up or not.
Yeah. Patrick? Because yeah, because this isn't. So 12 isn't in the domain, so we don't have to check on either side of it because it's just not in the domain. 9 is at the edge of our domain. There's not going to be any change of sign because you can't go to the right of 9. So it's just whatever the sign is to the left of 9. When we test at a point, it's negative. So it's going to be negative for the entire domain. All right. Perhaps one more point that we should concern ourselves with would be, let's see, we can do the Y-intercept. How do we find the Y-intercept? Yeah, let x equal 0. So g of 0 would be 0 times 3, which would be 0. So that's also coincidentally going to be your x-intercept. It's going to pass right through the origin. And it might be helpful to figure out one last point here, and that is right here. We know that there's a horizontal tangent at x equals 6, but what's the value of the function at x equals 6? Well, okay, plug it in. Let's find out. G of 6 is going to be 6 times the square root of 3, so whatever that is. Probably about, maybe 10 something? Yeah, I'm guessing about 10. All right. But there's good news for us here. We don't exactly have to, you know what? This graph doesn't quite look right. No, that's not the right one. All right, let's graph this then, putting together all that we've got. So we want to reflect a few things. We want to reflect the root, the concavity, and where it's increasing and decreasing. I didn't give myself enough room here. No, I think I'm going to try a different graph. You know what? Let's just use the graph that we had. I don't think the scaling is correct on this in order to use this. Let's do 2, 4, 6, 8, 10. And on the y-axis, I'll do likewise. Let's do 5 and 10 on the y-axis. I am going to take the time to figure out 6 times square root of 3. 10.39. All right. So it's a little bit above 10. So at 6, we're a little bit above 10. We can also see that at x equal 9, the function is at 0. It passes through the x and y axis right there at the origin. And it's perennially concave down. Now, there's nothing wrong with looking at the graph of this on your graphing calculator to kind of verify some of this stuff. But what I'm going to look to see is that your graph has the important features. And the important features for me would be the correct maximum point, any intercepts. We have 2 intercepts for the x-axis, 1 for the y-axis, and it has a concave down shape, CC down, throughout its entire domain. Nice. Any follow-up on Problem number 12 here. Certainly it's a challenging one. All right. Let's try some more here. Let's go all the way up to problem number 4. A little bit similar to one that we did earlier. Problem number 4 is y equals x squared plus 1 over x squared minus 4. Let's start as we always do. What's the first step in working with these types of functions? Domain. So the domain in this one is anything but what? Positive or negative 2. So x is not equal to plus or minus 2. Then let's look at any vertical or horizontal asymptotes. Now, the domain here kind of steers you in the direction of the vertical asymptotes. You're going to have vertical asymptotes at x equal 2 and x equal negative 2 are our vertical asymptotes. What about the horizontal asymptote? Yeah, x equal 1. All right, so actually not x equal 1, y equal 1 is our horizontal asymptote. If you're not quite sure about that one comes from the limit as x approaches infinity of x squared plus 1 over x squared minus 4. Because these two things because the numerator and denominator have the same degree, it's going to be the ratio of the leading coefficients that represents your limit. 1 over 1 gives you y equal 1 for your horizontal asymptote. What else can we look at? Well, we can look at the Y-intercept. So for the Y-intercept, set x equal to 0. If I set x equals 0, what do I get for the Y-intercept? Yeah, negative 1/4. If I set y equals 0 for the x-intercept, then I get 0 equals x squared plus 1 over x squared minus 4. This is going to equal 0 where the numerator equals 0. If you multiply both sides by x squared minus 4, it'll cancel here. Can you solve x squared plus 1 equals 0? Yeah. No solution. So there are no x-intercepts. It doesn't touch the x-axis at all. Okay, let's keep going. We need to play around with some derivatives here. And as much as I might like to, there's not really an easy way to avoid using the quotient rule. So, all right, let's just suck it up and use the quotient rule and deal with it. So our function, let me write it again up here. Start by squaring the denominator, and then the denominator times the derivative of the numerator. So x squared minus 4 times 2x, thank you, minus what? The numerator times the derivative of the denominator. So x squared plus 1 times 2x again. And we should clean that up a little bit. Here I'm going to distribute the 2x. Here I'm going to distribute a negative 2x. So I'll get 2x cubed minus 8x minus 2x cubed minus 2x over x squared minus 4 squared. Mercifully, we get a little cancellation and some simplification. Overall, you should get negative 10x over x squared minus 4 squared. That's our first derivative. Let's keep going and calculate the second derivative while we're in kind of this mode of calculating derivatives. For the second derivative, kind of like the first derivative, again, you have to use the quotient rule. So we'll start by squaring the denominator. X squared minus 4 squared squared again. So we'll have an x squared minus 4 to the 4th power. And then the denominator, which was x squared minus 4 squared, times the derivative of the numerator, which is minus 10. And then the numerator, so minus the numerator, which is negative 10x, times the derivative of the denominator. Derivative of the denominator is going to be a little bit of work here, isn't it? It's going to require the chain rule. So let's get at it. That's going to be a 2 times x squared minus 4 to the 1st power times 2x. You know what? It wasn't as bad as I expected. You're right. It wasn't that bad. Let me clean things up here in the numerator in maybe 2 steps instead of trying to do it all in one. Let's clean up all this stuff that's multiplying this binomial. I've got a minus and a minus. That's going to be a plus, a 2, and another 2, and a 10. So that's going to be 40x squared. So I'll have a plus 40x squared times x squared minus 4. Over here, I'm just going to factor out the negative 10. I'll put that out in front. In the denominator, let's just write that to the 4th power. Let's double check this. 2 times 2 times 10 is 40. The negatives cancel. And then an x and an x, 40x squared. Okay. Let's keep going. We still need to do a little bit more cleaning up with the numerator. Let me suggest you do it this way. Let's factor out the greatest common factor in the numerator. What can I pull out of the numerator? X squared minus 4, and let's also pull out maybe the 10. So I'm going to pull out 10 x squared minus 4. That's going to leave behind a negative 1 and an x squared minus 4. And I pulled out the 10, so it's going to leave behind a 4x squared. This term is gone altogether. That second binomial, I factored it out. Over x squared minus 4 to the 4th power. There's a couple things that we can clean up and should clean up. This will cancel with one of these, so it'll leave me with a cube in the denominator. I've got like terms in the numerator, so minus x squared and 4x squared are going to give me 3x squared. So overall, 10 times 3x squared plus 4 over x squared minus 4 cubed. Whew. Get out the oxygen bottle, right? All right. So that's the second derivative of our function. Three, right? Because minus 1. Okay. let's take stock of our derivatives now. We had the first derivative, which was g prime of x was negative 10x over x squared minus 4 squared, and g double prime of x is 10 times 3x squared plus 4. Oh, thank you. Yeah. You know, the software that goes with this is remarkably unsophisticated. All right. I want to know where these things can change signs. In the denominator, it can change signs at 2 and negative 2. In the numerator of our derivative, where can this function change signs? Where can this equal 0? At 0. So as far as the derivative is concerned, make ourselves a little chart. X, g prime, negative 2, 0, and 2. Okay, the derivative is 0 here. It doesn't exist at these points. That's fine. And let's test some points. I don't think I want to take the time to plug that into my graphing calculator. Let's just think about it. At 3, this would be negative, negative, positive, positive. So the function should be increasing, increasing, decreasing, decreasing. How about the second derivative here? This can only change signs where the denominator changes signs. So x, g, and g double prime. So really you can only change signs at negative 2 and 2. This one I think I will test in my calculator. So 10, 3x squared plus 4 divided by x squared minus 4 cubed. Some good test points would be, say, negative 3, 0. Well, I don't want to use 0. Yeah, I can use 0. And 3. So negative 3, 0, and 3. Plus, minus, and plus. So concave up, concave down, concave up. Wow, lots of information here. Let's see if we can't put it all together. You have a graph of this on the back of your handout. And look. Concave up. Thank you. So like I said, lots of information to put together for this one. On an exam, what I may do, depending on the problem, is I may give you either the first derivative or the second derivative, just to kind of help you out, because these problems, as you can see, can get very, very long. We had vertical asymptotes at 2 and negative 2, so let's sketch those in. We had a horizontal asymptote at y equals 1. So I'll sketch those in as well. I tend to like to put these in with dashed lines. I didn't with the first two, but it's just because these are not really part of the graph. They're just aids in looking at it and drawing it, but they're not really parts of the graph. We can sketch in our Y-intercept, which was at -1/4. So on this scale, that would be about here. Let's see, 1, 1/2, 1/4, about there. The graph does not touch the x-axis. That's okay. The graph is going to be symmetric with respect to the y-axis. To the left of the y-axis, the function's increasing. To the right of it, it's decreasing. You can look at the graph on your graphing calculator and try and draw things based on that. You should be reflecting some of the shapes that I have here. Now, I put these points on the graph just to help you draw something more accurate. So the graph has a concave up shape here. Between -2 and 2, the graph is a concave down shape. And then concave up to the right of x equal 2. Increasing, increasing until 0, then decreasing and decreasing. So it exactly matches all the different things from our graphs. And like I said, it'd be hard for me to give you a test with like a bunch of these problems unless I provide you with a lot of, a lot of the work already done for you in terms of calculating your first and second derivative. I tend to like to do that because any mistakes that you make, I want them to be because you show me that you don't understand something, not that you made a mistake with calculating a derivative. Because if you make a mistake calculating a derivative, it throws everything off. And I don't want to see you get points taken off because you made a mistake with the derivative. But if you're given the derivative, I'm hoping that you can work with the rest of this. Make sure you can find horizontal and vertical asymptotes, x-intercepts, y-intercepts. Understand where things are concave up, concave down, etc. And overall, make sure that your graph matches what you see on your graphing calculator. Boy? Oh, just stretching? Okay. All right. Test will be next Tuesday.